Hi, welcome to Unit 4, Day 1, Common Charges. So, in Unit 3, we learned about periodic trends, and there were quite a few periodic trends that we looked at. There's one more trend that's important for us to know, and this last trend is our common or ionic charges or oxidation state trend. So before we get into the trend, let's define what that is. So a common ionic charge is a charge an atom will likely have in an ionic compound. Now in this unit, we're going to learn what an ionic compound is, but an example of an ionic compound would be sodium chloride, also known as table salt. And if you look at table salt, it's made up of sodium ions, ions means something with a charge, and chlorine ions. So the sodium ions, if you look closely, they all have positive 1 charges, and that would be their common ionic charge. So sodiums typically have a +1 charge, and chlorine, on the other hand, has a -1 charge. So the common charge of chlorine is -1. Another example would be calcium fluoride. So if you look at calcium fluoride, what is the common ionic charge of the calcium, the Cas? Right, +2. And fluorines, or the fluorides, have a -1 charge. Okay, so how can we determine or predict that? Couple key things that we need to know in order to predict the common ionic charge. First thing is that atoms want a satisfied or full valence shell. All right. So what do I mean by that? A satisfied valence shell typically has 8 electrons, also known as an octet. So if you think of the octopus or ocho, just for 8 in Spanish, they all have the same root word. Octet means 8. There are 2 exceptions to that, hydrogen and helium, which are in period 1. And that's because for them, their valence shell is the first shell, which can only fit 2 electrons, so it's satisfied with 2 electrons. So the only exception to the octet rule are in the first period. Now, to get an octet, they can do one of 2 things. One thing an atom can do is it can lose all of their valence electrons. And in losing all of their valence electrons, that shell that used to be their valence shell has disappeared. And then the shell that is underneath it is a full or satisfied shell, that becomes their valence shell. So by losing all of their valence electrons, the next shell down becomes the valence shell, and that would already be a full or satisfied shell. The other thing an atom can do to get a satisfied shell, aside from losing all their electrons, is to gain enough to get an octet. So, for example, if an atom has 6 valence electrons and it needs to get an octet, it can gain 2 more to get to 8 electrons to get that octet. All right. So once again, 2 things they can do. They can either lose all their valence electrons or gain enough to get to 8. Now, the atom's going to do what's easiest. And when I say by what's easiest, I mean whichever is going to result in the least amount of electrons. Now, if an atom loses electrons, if the easiest thing for it to do is to lose electrons, it's going to have a positive common charge. And if the easiest thing for it to do is to gain electrons, it's going to have a negative common charge. Final couple things, metals typically have a positive common charge and non-metals typically have a minus common charge. So we're going to use the Bohr models to sort of help explain these common charges. And remember, the Bohr models, they show the darker circles here represent the nucleus, where you have your protons and neutrons. And the rings around it with the dots on it, those are our electron shells. And each dot represents an electron. Now, the valence shell is the outermost shell. So remember, we're always focusing on the outermost or valence shell. So for example, here, this is lithium. It has 1 valence electron. Where here we have beryllium, it has 1, 2 valence electrons. Okay, So let's take a look at an example of how we can use our understanding of the keys ideas of atoms wanting to either lose or gain electrons to get a satisfied or octet. Um, and we're going to start with this example, a group 1 element. So for group 1 elements, we're only going to focus on lithium on down. We're not focusing on hydrogen because remember its valence shell is in the first shell, which it's satisfied with 2. So we'll look at that later. So let's take a look at an element in group 1. First thing is, how many valence electrons does it have? They all have one valence electron. One electron in its outermost shell. Now, remember, to get a satisfied valence shell, it can either lose all or gain enough to get an octet. So if it's going to lose all of its electrons, that means it has to lose the one electron it has. Now, how much does it need to gain to get to 8? So if it has 1, it needs to gain 7. All right, once we know how much it needs to lose or gain, the next question we need to do to figure out the common charge is figure out what's the easiest for it to do. Well, what's results in the least amount of electrons? Losing the 1, right? So with that being said, it's going to lose, elements in group 1 are going to lose 1 electron because it's easier for them to do that than to gain 7. And since it's losing 1 electron, elements in group 1 are going to have a common charge of +1. So recall that if you lose electrons, if an atom loses electrons, it becomes more positive. So it lost 1, it'll become +1. Let's take a look at another example of so group 15 that has 5 valence electrons, and it can either lose all 5 or gain enough to get an octet of 8. So if it has 5, how many more does it need to gain to get to 8? 3. So what's going to be easiest for it to do? Lose all 5 valence electrons or gain 3? Of course, gain the 3 because that's the least number of electrons that needs to be changed. So in that case, easier for it to gain 3 than to lose, that should say 5, not 7, sorry, to lose all 5. And so with that being said, group 15 will gain 3 electrons. And if it gains 3 electrons, it's going to have a -3 common charge. So elements in group 15 have a -3 common charge. Now let's see if you can do that with elements in group 13. So first thing is you're going to determine how many valence electrons it has. How many is it going to lose? Does it need to lose, or how many does it need to gain? And then choose the one it's going to prefer to do. Once you know how what it prefers to do, whether it prefers to lose a certain number or gain a certain number, use that information to determine the common charge. So pause the video now. When you press play again, the answer will be revealed. All right, so group 13, it has 3 valence electrons, 1, 2, 3. It can either lose all 3 or gain enough to get to 8. That would be gaining 5 more. So if it has 3, it needs to gain 5 more to get to 8. The easiest thing for it to do is to lose the 3 since that's the smallest number. And so with that being said, if it's going to lose electrons, it's going to have a positive charge. So it would have a +3 common charge. So group 13 elements have a +3 common charge. Okay, try it now for group 18, and we're going to once again skip the element in period 1, so helium, because elements in period 1, their valence shell is the first shell, so we're going to skip those. So you're going to look for at these on the bottom here, figure out what its common charge, the common charges of element in group 18. Pause the video now and then press play again, the answer will be revealed. Great, so these all have 8 valence electrons. So they could either lose all 8 or gain nothing because they already have their octet. So noble gases have an octet, so they don't need to lose or gain anything. And that's the reason why noble gases don't form bonds and they're not reactive, okay? So in terms of common charges, noble gases will have a common charge of 0 because they don't need to lose or gain. They are already satisfied. All right, so the exceptions, once again, to this will be hydrogen and helium. Remember that they're in the first period. Their valence shell is the first shell, which can only hold a maximum of 2 electrons. So that's what they'll be satisfied with, 2 electrons. And common charges for hydrogen are it's +1 or -1. The reason why that is because hydrogen can either lose the one that it has, or it can gain 1 to get a full shell of 2. And in its case, losing 1 or gaining 1 is the same number, so the common charge for it will be plus or minus 1. Now for helium, on the other hand, it's a noble gas. It already has a satisfied shell, so its common charge is 0. All right, important things to know. You have to memorize or know just from the number of valence electron the common charges. There's sort of a pattern there. You start with +1, then it goes +2, then it goes +3, then it goes +4, and then you can't go anymore. So +1, +2, +3, +4. Then it starts to go down from the negative side to -3, -2, -1 to 0. So you have to know these common charges. The transition metals, their charges vary, so there's nothing to memorize there. Just know that their charges vary. They don't have common charges. All right, let's try this last CFU. So potassium oxide is an ionic compound. What's the common charge of potassium? What's the common charge of oxygen? First, you want to determine what group it's in. So I've highlighted it for you to make it a little easier. And once you know what group it's in, what common charge will it have? So remember, the group determines its common charge. So pause the video now, and when you press play again, the answer will be revealed. Great, so potassium will have a +1 charge because it's in group 1, and oxygen will have a -2 charge because it's in group 16. Remember, it goes +1, +2, we skip, +3, +4, then -3, -2. Right, so this one's -2. All right, so important for Unit 4, you have to know common charges. This is super duper important, so make sure you memorize it. That's it for this video. Have a quality day.